All right, so this week we're going to take a look at two sections. We're basically going to split the two sections into 3 days. Today's section we'll do over two. The next section we're only going to really do half of it. So really, actually, it's only like 2.5 sections. We'll do a review day on Thursday and then the test on Friday. So we're going to start by talking about right triangle trig. You've probably done a little bit of that in geometry, but we're going to go into a lot more depth, especially in the second half of this section, looking at inverse trig functions, and then in chapter 7, we're going to start looking at the graphs of inverse trig functions. Today might be a little bit of a review, but I want to start out just by talking about what is a right triangle. Okay, so what does it mean if you have a right triangle? Yeah, it has a right angle, which is a 90-degree angle. So this week, all the trigonometry we're going to be doing is going to be based on having a right triangle. In chapter either 7 or 8 later on, we're going to be doing everything we're doing again right now, but we're going to do it when we don't have a right triangle. Okay? When you have a right angle or a right triangle, it does make things a little bit easier because there's certain theorems you're allowed to use, and we'll talk about what those are. Okay, the side opposite the right angle, that's the hypotenuse. And what's special about the hypotenuse in a triangle? Yeah, Josh? Yeah, it's always the longest side. Okay, it should always be the longest side. What are the names of the two other sides? The legs. Okay, and the legs are always shorter than the hypotenuse. And does anybody know the relationship between the sides in a triangle in terms of, like, if I just gave you 3 numbers, like 1, 2, 7, and I said, could those 3 sides make a triangle? Does anybody know that the test to see if any 3 numbers make a triangle? Yeah?
The 2 legs can be more than
No, the 2 legs have to add up and be more.
Yep, in fact, that's true for any sides. If you add any 2 sides, they have to be bigger than the 3rd side. Right? So if I gave you sides 1, 2, 7, no. So that could not make a triangle because if you add the 1 and the 2, it's not bigger than the 7. Okay, so that's the test to see if 3 numbers form a triangle. Add up any 2, and it has to be bigger than the 3rd. If it's not, you don't have a triangle. Okay, so here's a diagram of basically what we just said. Hypotenuse across from the 90, the 2 legs. Normally we label the sides using English lowercase letters, A, B, C. And then I've marked this angle in the lower right. In this particular case, I'm just calling it theta. And I'm saying that it has to be an acute angle. Now, I wrote the definition here. An acute angle is an angle between 0 and 90. But how come this has to be acute? Why does it have to be between 0 and 90?
This triangle only ends up to 180.
Okay, so a triangle has it to 180. And you've already used the right angle for the 90. So out of the 180, all that you have left is 90. So this angle has to be less than 90 to leave a little bit for the 3rd one. Okay. All right. So when we are dealing with sides of a triangle, as long as you know 2 out of the 3, you can find the 3rd one using the Pythagorean theorem. And there's a proof we can do of the Pythagorean theorem. I don't think we're going to do it today, but maybe when we start class one day, like as a warm-up or going over the homework, I'll show you the proof. It's very simple, especially the way I do it, because there's lots of ways you can prove this theorem. But there's a really simple way. We're just drawing a picture with some triangles and a square. What is the Pythagorean theorem? What is that theorem? Yeah?
A squared plus B squared equals C squared.
All right, so the formula a lot of times is a squared plus b squared plus c squared. Can you explain what that means in words, though, without using variables?
If you square both the legs and add them together, it equals the hypotenuse squared.
Yes. So if you call the 2 legs a and b and the hypotenuse c, then it's exactly what Josh said. But in general, if you don't use a, b, and c for the sides, It's leg squared plus leg squared equals hypotenuse squared. Okay, my version, the way I wrote the theorem, goes with the picture, because I used A, B, and C. Okay, if we have time, I'll come back to this, but this is the picture that you can use to prove the Pythagorean theorem. Basically, you've got like a square here, and if you look at it, you've got 4 copies of that triangle. Right? And the goal is to look at finding areas. Okay, well, let's just do it real quick. I didn't practice it this morning, so hopefully I remember how to do it. Let's find the area of the big square. Okay, how would you find the area of this? Actually, you know what? Let's, I'm trying to think. Let's start with finding the area of the small square, the one inside. What's the area of that small square? The one, I'll put it like in green. Yeah, the area of that is just c squared, right? Just c times c. Okay, so small square area is c squared. Everybody agree with that? Okay. Now I want to find the area of the small square in a different way. What I want to do this time is I want to find it by looking at the big square area and then subtract all the triangles. Okay, if you do it that way, that's still the small square. Okay, I'm going to find this area, and then I'm going to subtract this, 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 and that. Okay? Does everyone agree if I do that, that will be the area of the small square? It's just a different way to find it. Okay? So, what's the area of the big square? Yeah? So area of big square is A plus B. Okay, and then you square it. All right. Now let's find the area of one of the small triangles, and we have 4 of them. Okay, so we'll have to subtract 4 of it. All right, so let's find the area of triangle. So the area of a triangle is 1/2 base times height. Okay, let's focus on this one. Okay, so the area of that triangle is 1/2. What's the base of that triangle? Yeah, A, or it depends on how you look at it. And what's the height? B, if you kind of were to stand it up. So it's 1/2 AB. All right. So now I'm going to find the area of the small square again by doing some subtraction. Area of small square. It's going to be the area of the big square. Big square minus, and what am I going to subtract from that? Yeah, I'm going to subtract 4 times the area of the triangle. Okay, and when I'm done, whatever I get here is equal to what I got right there. Okay, because they're both the area of the small square, just different ways of finding it. Okay, so the area of the big square is A plus B squared. What's A plus B squared? Yep, it's A squared plus 2AB plus B squared minus 4 times the area of the small square, 1/2 AB. A squared plus 2AB plus B squared. What's 4 times 1/2? 2AB. And now what happens? Yeah, I have minus 2AD plus 2AB, and I get the area of the small square according to this formula is what? A squared plus B squared. But I had a different formula for the area of the small square earlier, C squared. But they're both the area of the small square, so that means that they are what? They're equal to each other. So I can say that A squared plus B squared equals C squared. Okay? Where A, B, and C are the sides of this triangle. A is the short leg, B is the long leg, and C is the one across from the knife. That's actually a very, very straightforward way to prove the Pythagorean theorem, one of dozens of ways. And it doesn't require anything more than really algebra 1. And a little geometry. Okay, any questions on that? And now this formula, the Pythagorean theorem, this is used when we get to more advanced stuff in trig to make tons of other formulas. All right? So if you can prove this one, this is kind of the basis for a lot of other different formulas in trig. All right, so we're going to use the Pythagorean theorem. Not quite yet, but we are going to use it a lot in this section. Okay. So I'm going to look at the definitions of the 6 trig functions, but this time we're not going to do it the way we did with unit circle trig. Okay, with unit circle trig, we had sine was y, cosine was x, and tangent was y over x. People kind of remember that a little bit? That's how we did it with unit circle trig. And we always worked with angles that were multiples of 30 and 45. Well, now we're going to define the 6 trig functions using the words opposite, adjacent, and hypotenuse. So from geometry, does anybody know what the sine is equal to? Yeah? Yep. So sine, you want to write it, sine is opposite over hypotenuse. How about the cosine? Cosine is adjacent over hypotenuse. And how about the tangent? Opposite over adjacent. Okay, so have people seen that before as a way to remember? Yeah, Sakatoa. Okay, I had somebody before when I asked, how can you remember these? And they said Sacagawea. And I said, no, she's not going to help. So Sakatoa will, but not Sacagawea. So these are the 3 trig functions we use most often. And when we get to solving a right triangle, which means finding out how big are all the sides, how big are all the angles, these are the only 3 we're going to use. But there are 3 other trig functions. And what's the relationship between the trig function I have on the left and the trig function on the right in every row? Yeah, they are the reciprocals. So to get the reciprocal, what does that mean you do? You flip. So that means the cosecant would be what over what? Yeah, hypotenuse over opposite. How about the secant? No, Tom, what would the secant be? Yeah, hypotenuse over adjacent. And Zach, how about the cotangent?
Adjacent over opposite.
Adjacent over opposite. Okay, the 3 on the right are not used as much, but they are trig functions, and we can use them, but we just don't use them as much. Now, the terms opposite and adjacent are what we call, they're relative terms. Does anyone know what I mean by that, being relative terms? Yep.
It all depends on triangles.
Yeah. It doesn't tell you exactly a side unless you have a specific diagram you're looking at. It's like if I said to you, go left. Well, left can be different depending on which way you're facing. Okay, like if I'm facing you, left is the door. For you, though, left is the window. Okay, left and right are relative terms depending on how you face. Okay, so if we have a triangle, And let's say we are standing here. Okay, this is like the way we're facing. We're standing in this corner of the triangle looking out. Whatever your side that is across from you, that's opposite. And the side that's next to you is adjacent. And you might look at this and say, well, wait, there's two sides that are next to me. Well, this side is the hypotenuse. Okay? Now, opposite and adjacent switch places if you switch where you're standing. Okay, so pretend like you're standing here, and now you're looking out from that corner. Okay, the side that's opposite would be at the bottom, and the side that's adjacent is over here. What happens to the hypotenuse when you switch where you put your perspective? Nothing. Okay, the hypotenuse is more of what we call an absolute term. It doesn't change depending on which way you're facing. Okay, so with my analogy earlier, that would kind of be like up for all of us. As long as you're standing, with your feet on the ground, up is always towards the ceiling. It doesn't matter which way I turn. Okay. Left and right change, but up doesn't. Okay, that's kind of like the hypotenuse. So any questions on those six trig functions? All right, so what I want to basically look at now is the fact that it doesn't matter the size of a triangle that you work with when you're doing trig. For example, if you take a 30, 60, 90 triangle that's small, or you take a 30, 60, 90 triangle and enlarge it, I'm going to find a trig function of one of these angles. And whether I do it in the small triangle or the big triangle, it's going to come out the same. Okay, it doesn't matter. So how about, Amanda, it doesn't matter. Let's just pick one of these angles to work with. Not the 90, though. Either the 30 or the 60. All right? So let's do 30. And let's find it doesn't matter which one we do, but let's do the sine of 30. Okay? I'm going to do the sine of 30 in the small triangle. And then I'm going to do the sine of 30 in the big triangle. And let's see what happens. So sine is opposite over hypotenuse. What side is opposite the 30? And what's the hypotenuse? 2. So in the small triangle, the sine of 30 is 1/2. And that is a to scale the best I could diagram. These are actual numbers that would make a 30, 60, 90 triangle. These aren't just random numbers I picked. And now let's look at the same triangle, just enlarged. What's the opposite side here? 2. And what's the hypotenuse? And what does that reduce to? 1/2. Okay, so the point is that the sine of 30 is the same in every single triangle, regardless of the size. Okay? That's what this is saying right here. So trig functions always have the same value for a given angle. Okay. Any questions on that? Okay. In general, I think it's easier to work with smaller triangles than bigger triangles. Because usually smaller triangles, you don't end up having to reduce the sides at the end. A bigger triangle, you might have to do that. And even though I just did this with the 30 and I just did it with sine, I could do it with any one of these 6 trig functions, and I could do it with either one of these angles. And it would work. You'd get the same answer every time in both triangles. All right, so how do you find the 6 trig functions if you are given one of them? Anyone? Before I show you how to do it, anybody have a thought how you would do it? Like if I tell you that, all right, I have some angle, which we're never going to know. Okay, we'll call it the mystery angle, theta. And the sine of that mystery angle is 5/6. I want to know every other trig function. I want the cosine, I want the tangent, everything else.
Couldn't you draw a triangle, and then because sine is opposite over hypotenuse, we know that the opposite side of the angle is 5 and then the hypotenuse is 6.
Yeah.
So we could do the Pythagorean theorem.
Right. We can put theta wherever we want. It doesn't matter if you put theta at the top or over on the right. But the point is exactly what Amanda just said. Okay, take what you're given, draw a diagram, and use it to label 2 of the sides. Because as long as they give you one of the trig functions, it's always going to be a fraction. And even if it wasn't a fraction, like let's say they said the tangent equals 2. Well, you could make it a fraction. Just put it over 1. So take what they give you, use it to label 2 sides of the triangle, and then use the Pythagorean theorem to get the third side. So in terms of writing stuff down, that's really all you need to write. Once you do that, then I'm just explaining what the situation is now. You know all 3 sides, and then you could find any trig function you want. Okay, so they could give you any one of the 6 trig functions to start with. But they got to give you at least one of them. All right, so let's go over here. And they said, this time the sine is 5/6. So let's put theta, let's put it in the lower right. So I'm going to put theta there. And as Amanda said, sine is opposite over hypotenuse. And now using the theorem we proved earlier, a squared, this Pythagorean theorem, we can find the third side. Okay, can somebody set up my Pythagorean theorem for me to find the third side? Yeah, Amanda?
Wouldn't it be 5 squared plus b squared equals 6 squared?
Yeah, 5 squared plus b squared equals 6 squared. Right? And you could call the bottom side a, b, x. You can call it anything you want. The point is we're going to have a number for it in a second. So we decided to call it b. So 25 equals 25 plus b squared equals 36. Try to make that look more like a 6. And now b squared, if I bring the 25 to the other side, would equal how much? 11? So what's b? And so b is the square root of 11. Now, we got to be careful when we do the trig functions, because something could happen with this square root that we would have to fix. What could happen with that square root that we couldn't leave in the final answer? Yep. Right. It could end up in the denominator. Anytime it ends up in the denominator, we need to fix that. Now, through this whole process, we are never going to know the size of this angle. We're not asking the size of the angle. Okay? And on the test, some people get tripped up with the difference between what's the sine of theta and then this question. What is theta? One is a trig function. One is the size of an angle. Okay? I am not asking for the size of an angle here. I could find it, but not here. Okay? So let's just find the trig functions. Okay. Sine, we already know. That one was given. Okay. What would be my cosine of theta? Square root of 11 over 6. And tangent of theta would be 5 over square root of 11, but we do need to fix that so the root's not in the bottom. Yeah, and we did this before when we did unit circle trig. Now, to get the other 3 trig functions, what am I going to do with each of those? Yeah, I'm just going to flip them. Okay, so what I'm going to do, I'm just going to make that a little smaller. All right, so what trig function, when you flip sine, what trig function does that give you? Cosecant. And the cosecant would be 6/5. How about when you flip the cosine? secant. And what would the secant be? Over 11. Yep. And now your cotangent, you have two choices of things you can flip. The first fraction or the second fraction. They're the same. Okay, that's why they have an equal sign between them. Which fraction is better to flip, the first one or the second one? Yeah, why should you flip the first one? Yeah, if you flip the first one, you're done. Okay, if you flip the second one, the square root's going to go back to the bottom, and then you need to fix that whole thing again. Okay. Questions on that? Okay, that would be 6 separate problems on a test. I'm not going to ask you to find all 6 trig functions in one problem, but I could just draw a diagram and say, tell me the secant of theta. Okay? And keep in mind, I'll always tell you where to put theta. If I don't tell you that, you don't have a reference point for opposite and adjacent. Okay, did anyone know the hypotenuse of this one? 13. How do you know that? Yes, this is a Pythagorean triple. What does that mean? Well, what is it, if you have 3 numbers, what does it mean if they form a Pythagorean triple? Anybody know what that, yeah?
There are multiples also. Pythagorean triple.
Well, I know what makes something a triple though? Is that last problem a Pythagorean triple? How come? What makes that one not a Pythagorean triple?
They need to be integers.
Yes, a Pythagorean triple is where all the side lengths are integers, no decimals. All right, so in this case, if you did 5 squared plus 12 squared, you get 169, and the square root of it is 13. Okay, there's an infinite number of Pythagorean triples. 5, 12, 13 is one. 3, 4, 5 is another. Those are the 2 that I know off the top of my head. But if you had a 3, 4, 5, a 30, 40, 50, that's not a different Pythagorean triple. How come 3, 4, 5 and 30, 40, 50 aren't different? It's just a larger version of a 3, 4, 5. Okay, so we don't count larger and smaller versions. A 5, 12, 13, that is not a larger version of a 3, 4, 5. The side lengths are different ratios. All right? But there's still an infinite number of them, and if you go on Google, you could just type in Pythagorean triples, and you get thousands of them. But this is one of the most basic ones. And what's nice is we're not going to have any roots. Okay, so it's going to make finding the trig functions a lot easier. So Alyssa, what's the sign here? Let's see. Yep. 5 over, what did you say?
12.
That's going to be my tangent. 5 over 13. So opposite over hypotenuse. Okay, Rachel, how about my cosine?
It would be 12.
Yep, adjacent over hypotenuse. And the tangent, I just said that was what we said earlier. It's 5 over 12. And now, Francisco, to get the other 3 trig functions, what do I do with those? Flip them. So my cosecant is 13/5. My secant, 13/12. And my cotangent, 12/5. Any one of these 6 pieces of information is enough to find the size of that angle, if I really wanted to. Okay. Especially if you tell me that it's an angle in a right triangle, because then I know it has to be less than 90. And that's important because there's actually 2 angles. Like let's say I was using sine to find the size of this angle. There are 2 angles that would have a sine of 5/13. One of the angles is in quadrant 1. One of the angles is in quadrant 2. But I know it couldn't be the quadrant 2 answer because quadrant 2 angles are between 90 and 180. That would be too big to fit in this triangle. All right, so how I figured out that second answer, we're going to talk about that tomorrow. Because when you're doing an algebra problem that doesn't have anything to do with a triangle, I might want both answers. Right? Not just the answer that would fit in the triangle, but the other answer that would work algebraically. Right? But we'll talk more about that tomorrow. Did anybody do that in geometry last year? How you figure out the angle here that would give you 5/13 for the sine? That gets into inverse trig. All right, so now I'm giving you an angle, and I want to find the 6 trig functions of 45 degrees. Okay, so I've drawn a 45, 45, 90 triangle. But in order to find the trig functions, I need to label the sides. Now, does it matter the size of the 45, 45, 90 triangle I use? No. We saw earlier that you can use larger or smaller versions of the same triangle, and this doesn't matter. Okay, so I just need somebody to give me numbers here for the sides, but they can be any size you want as long as they are correct for a 45, 45, 90. So what would be some easy numbers to work with? I would probably start with the legs. Yep? Sure. Now why did you make them both the same? Yeah. In a triangle, if angles are equal, the sides opposite those angles are equal. So you can pick any two numbers you want for the legs as long as you keep them equal. Because that always happens in a 45, 45, 90. And now, I still need the third side though. So how would I get that? Yeah. Yep, this would be square root 2. So if you don't know the special right triangles, you just use your Pythagorean theorem. Now you have an accurate diagram of a 45, 45, 90. You can find all 6 trig functions. Okay, let's just do the first 3. I'll leave the next 3 up to you because all you have to do is flip them. Now, I want to know the trig functions of 45 degrees. So which 45-degree angle should I use as my reference point? It doesn't matter. You're going to get the same answers either way because the 2 of the sides are the same. So let's use this as our reference point. Okay, but it doesn't matter. Okay, Taylor, what would be the sine of 45? 1 over the square root of 2. And how would you fix that so the root's not in the bottom?
1 square root of 2 over 2.
Yep. So square root of 2 over 2. Now, what about the cosine of 45? And actually, you know what? Instead of writing theta, I know what theta is this time. It's 45. Okay, so what about the cosine of 45? It's the same thing. Because the opposite and adjacent sides here are the same thing. So I don't have to go through the work again. I can just copy the answer I had up above. And that's cosine. Which is also nice because when you find secant and cosecant, those are also the same. Because you're flipping the same thing. And how about the tangent? 1. 1 divided by 1, or 1. And when you flip 1, what do you get? 1. Okay. So 1, there's 2 numbers you can flip and they stay the same. If you flip the number 1, it stays the same. And what other number? Yes, -1. Either one of those numbers, when you flip them, they stay the same. So 45, 45, 90 triangles, those are pretty common and we work with those a lot. Okay, the next triangle we work with a lot is a 30, 60, 90. But we need a diagram of a 30, 60, 90 in order to find the trig functions. So I'm starting you off with an equilateral triangle to give you a hint at how to draw a diagram for a 30, 60, 90. That's not a 30, 60, 90. That's an equilateral triangle. Okay, but any thoughts what I can do to that triangle to turn it into a 30, 60, 90? Okay, and I'll do it here and then I'll draw it separate so we don't have to look at the original.
What did you just say? I don't know what it's called, I don't remember what it's called, you just kind of like draw a line down
Yeah, we're going to draw, since it's an equilateral triangle, it's called a lot of things. We're going to draw an angle bisector from here. It's also called a segment bisector or an altitude. It has all kinds of names. But the point is, you could prove that by just drawing this segment, these two triangles are congruent. Okay? The simplest way to prove it would be side, side, side. That side is, oops. That side is congruent to that side. That side is congruent to itself. And technically, well, it depends on what you already have proved to this point in geometry. If you know in an equilateral triangle that if you draw a segment from the vertex to the opposite side and it's perpendicular, it does bisect the other two sides. So if you knew that, then you could say this side is congruent to this side, which means you just created two congruent triangles, which then means if this original angle, well, how much is any angle in an equilateral triangle? 60. But if you drew this in and it created two congruent triangles, that means this angle at the top is now 30, and this angle at the bottom has to be 60 because they all add up to 180. All right, so now off to the side, I'm going to draw just that left-hand half of it. So this side is 2. What other side do I know in that diagram? Yeah, what's the base? Yeah. Because I bisected that third side into two equal parts, each part must be 1 unit. And now, how could I get the height? Yeah, Josh? I could use the Pythagorean theorem. Does anybody know what the height will come out to here? Yeah, it's the square root of 3. So now, just by using a little bit of geometry and Pythagorean theorem, we have an accurate drawing of a 30, 60, 90 right triangle, which will allow us to do what they want. Okay, so let's find the trig functions. And let's start with 30 degrees. And I am going to do them all because I want you to see a connection here. So what's the sine of 30 degrees? Well, Andrew?
1 over 2.
Yep, opposite over hypotenuse, so it's 1 over 2. So let's do the cosecant at the same time. 2. That's a nice one because there's no roots. Right, let's do the cosine of 30. How about, Jeff, what would be the cosine of 30?
That'd be 2 over 3.
That would be the secant.
Oh, okay, so it'd be 1 over 3.
That would be the tangent. I should start writing these down. So 1 over the square root of 3. I'll get back to secant. I forgot what you said exactly. But cosine is adjacent over hypotenuse.
Okay, that would be square root of 3 over 2.
Square root of 3 over 2. And then the secant, I think you had said that one earlier, would be 2 over the square root of 3. But then we have to fix it. The tangent is opposite over adjacent, which would just be square root of 3 over 3. And my cotangent would be how much? Just the square root of 3. Now those are the 6 trig functions for 30. Let's look at what happens when we do 60. Anybody think they already know what's going to happen when I do it for a 60? Because I'm not using a different triangle. 30 and 60 are in the same triangle. So what happens? You think they know? Yeah? Yeah, the sine and the cosine are going to switch, the secant and the cosecant are going to switch, and the tangent and cotangent are going to switch. Because you've changed your reference point. Instead of standing at the 30, now you're standing at the 60. So you just switched opposite and adjacent. But you're going to get all the same answers. So now the sine of 60 is opposite over hypotenuse. So it's square root 3 over 2. And that means the cosecant is 2 root 3 over 3. Cosine is adjacent over hypotenuse. Adjacent is 1, hypotenuse is 2. So the cosine of 60 is a half. And the secant of 60 would be 2. And lastly, the tangent of 60. Tangent is opposite over adjacent. So it's root 3 over 2. I'm sorry. What did you say? Oh, yeah, root 3 over 1. Thank you. Yeah, so it's just root 3. And the cotangent, root 3 over 3. So exactly what we said earlier happens. The sine and the cosine, those answers switched. The secant and cosecant, those answers switched. And the tangent and cotangent, those two switched. Does anybody see a pattern with which trig function switched places? Sine, what's the connection between sine, cosine, secant, cosecant, tangent, cotangent? Yeah. Oh, what do you mean? Can you be more specific about their names?
It's sine and cosine, so one has a co in front of it, and that goes together.
Exactly. One has a co in front of it. So what ends up switching places here are what we call the cofunctions. So the cofunctions switch places. So sine, cosine, secant, cosecant, tangent, cotangent. Tangent and cotangent happen to be reciprocal functions and cofunctions. They're both. And I think I mention exactly what cofunctions are in a second, but that's the idea I wanted you to see in this problem. And what do you notice the connection between 30 and 60 is? What kind of angles are those? Another pair would be like 70 and 20. Or 10 and 80. Yeah, these are complementary. So there's a special pattern here when you have angles that are complementary and you look at cofunctions. Okay, and we're going to look at that right now. So first of all, the two acute angles in a right triangle are always complementary. Meaning they add up to 90. But why is that true? How come alpha plus beta is always going to be complementary? Yeah?
Because you have to add up to 180 with the goal, if you have a 90-degree angle.
Yep.
So the two have to add up to 90.
Exactly. Everybody get that? Okay. So they all have to add up to 180. You've already used 90 for the right angle. Now, the other thing I'm going to do is I'm going to label things a little differently than the book. I'm going to use the sides the same way the book does, lowercase a, b, and c. But for the angles, I'm going to use Greek letters. The angle across from A, I'm going to call alpha. The angle across from B, beta. What the book does is they use capital English letters for the angles and lowercase English letters for the sides. Why do you think I'm going to stay away from using capital English letters and lowercase English letters? There are a couple reasons. Yeah?
Well, like some letters are like almost exactly like the capital, so like a C, like there's like a little bit of size.
Yeah, if I don't have a reference like in a sentence, I can't tell if you just draw a C by itself, if it's capital or lowercase, right? And the other reason too is if you ask me like, what is A in a problem? Then I'd have to say, do you mean lowercase a or do you mean capital A? But by doing it this way, if we ever say a Greek letter, that's an angle. English letters are sides, and that'll eliminate quite a bit of confusion. We don't need a name for the angle across from C because it's always the right angle. So for now, it's always just the 90. When we get into triangles like this, where we don't have a right angle anymore, then we're going to have to give a name to that one. Okay, but not yet. And this idea, we already kind of looked at a little bit with the 30 and the 60. We didn't actually prove it, and I'm not going to really go through the proof right now, but I showed you an example of it with the 30 and the 60. If you take cofunctions, so cofunctions are like sine, cosine, secant, cosecant, tangent, cotangent. Those are your pairs of cofunctions. So if you give me two cofunctions, and then you give me two angles that add up to 90, complementary angles, the two answers would come out the same. Okay, so as an example, what's the cofunction for sine? Cosine. And what's the complement of 10 degrees? 80. These are cofunctions, and these are complementary angles. So if I type both of these into a calculator, they should come out what? Yeah, they should come out equal. Okay, cofunctions of complementary angles are equal. And you could check it. The sine of 10 is 0.1736. The cosine of 80 is 0.1736. Okay, so they come out the same. How about, what would the tangent of 20 be the same as? It would be the same as cotangent 7. Cofunctions, complementary angles. So where you can use that idea, does everybody have the complementary angle theorem? It's right here. I have the sine of 35 minus the cosine of 55. What's the relationship between sine and cosine? They're cofunctions. And how about the relationship between 35 and 55 if they were in the same triangle? They're complementary. So I have cofunctions of complementary angles, which means this and this are what? They're equal to each other. I have no idea what the sine of 35 is. I really don't. I don't know. It's a weird number. But I don't need to know what it is. All I know is I'm subtracting two things that are the same. So what do I get? 0. Okay. So that's a place you could use the theorem I just showed you. Okay. Actually, I think we might have done this exactly up above. What are tangent and cotangent? The cofunctions again, 20 and 70. Complementary. So if you compare what's on the top to what's on the bottom, they're the same thing. I have no idea what the tangent of 20 is or what the cotangent of 70 is, but they're the same thing. And if you divide two things that are the same, you get 1. So this trick works. This trick works with subtraction. It works with division. Would it work with addition? If you add two things that are the same, do you always get the same thing? No, you get the thing doubled, whatever it is. And how about multiplication? If you multiply two numbers that are the same, do you always get the same answer? No, you get the thing squared. So you can't really use the trick with addition and subtraction. I mean, you can only use the trick with addition and subtraction. Subtraction and division. This one is really kind of the same thing. You just do what's on the inside first. So what do you get when you divide what's on the inside? You get 1. And then you just do the arithmetic. So you pretty much always get an answer of 0 or 1. 0 if you do subtraction, 1 if you do division. Or if you put in like a +3 or a ×2, then you can change the answer. Right, but that's pretty much all you could do to it. Any questions on that? Yeah.
This is a weird question. Can you scroll up? So like, if you had like a sine of 45, could you figure out what it is equal to in cosine and then subtract?
Yeah, you could, so if you had the sine of 45, what's that equal to? Yeah, that's the same as the cosine of 45. Those two are the same.
And then would the answer to, like, if you did cosine of 45 minus cosine of 55, would it be cosine of 10?
Oh, no.
Okay, so
Yeah.
we never have to do that?
Yeah, you can't combine, yeah. So, like if you had like sine of 50 minus sine of 40, I get what you were saying, trying to almost make like terms. Yeah, you can't say that's the sine of 10.
Okay, so we never have to do that?
You wouldn't have to find the sine of 10 that way. In fact, I would never give you 10. I would give you angles that are multiples of 15, but that's a totally different way to do it. Nothing at all with what we're doing right now. We know how to do angles that are multiples of 30 and 45 right now. We did that on the unit circle. We don't know how to do the 15s yet, but we will probably in either chapter 7 or 8. Not yet. Okay. Any other questions? All right, so I think as far as homework goes, this is where I'm going to stop. But there's one more thing I'm going to have you write in your notes so we don't have to write it tomorrow. Okay, and I'll put that up for the homework in a second. Because tomorrow's lesson is a little bit longer, so anything we don't have to write tomorrow will save us a little bit, but I'm not going to give you homework on this part tonight. So when we start looking at problems that say solve the triangle, okay, when they ask you to solve a triangle, all that means to do is find out how long are all the sides and how big are all the angles. And we're always going to be solving right triangles. So if you're always solving a right triangle, what does that mean every single problem we solve is going to have in common? We're always going to have a 90-degree angle. But you need more information than that, okay, if you're going to solve the triangle. Does anybody know what I have to give you in order to be able to figure out all the sides and all the angles? The minimum I have to give you. And there's actually two cases. I can do two different things.
And then they're giving us a trig function. So like sine of theta.
Okay. So if I gave you a trig function, that would be like I'm giving you two sides. Yep, that's one way I can do it. I can give you two sides. Or, what else could I give you? For a right triangle. If I want you to solve it, in addition to the 90-degree angle, I can either give you the two sides, or I can give you two other pieces of information. And you could still solve it. Two angles? I couldn't give you two angles, because if I did that, like let's say I gave you this triangle, and I said this is a 30, this is a 60. Could you find the side lengths there? No, because you don't have a side for reference. I mean, we looked at two different 30, 60, 90 triangles earlier, where the sides were bigger and smaller versions. So I can't give you two angles. So that kind of narrows it down. I either give you two sides, or I give you a side and an angle. And how you go about these two situations is a little different. What's the theorem that we proved earlier that has to do with all the sides? Yep, so as we're solving right triangles, I want you to keep that theorem in mind. That's a theorem you can use. And what's another fact about triangles you can use that has to do with the angles? We've already used it a couple times today. Yep.
The interior angle of the triangle has 1, 2, 3, 3.
Right, all the angles add up to 180. And what would be, so that's called the triangle sum theorem. All the angles add up to 180. What's a corollary to that? It's another idea that's almost exactly the same idea. But instead of saying all the angles add up to 180, what else could you say? A little simpler idea based on that. Yep.
Alpha and beta equals 90.
Yeah, the acute angles add up to 90. Okay, we already said that earlier. Right? And that's a corollary to the triangle sum theorem. The acute angles in a right triangle add up to 90. So either way you want to think of it. Right, so that's what we'll start off with tomorrow. Okay, I'll recap that real quick, and then we'll go into actually solving a right triangle, where they give you some information to start with. Okay, does everybody have that? Good. Okay, so the homework tonight, there will not be any solving right triangles on it. It's going to end with the complementary angle theorem. So it's 361. 1 to 14, that's finding trig functions. So like finding the sine is problem 1, finding the cosine is problem 2, so they're actually pretty fast. 16 to 20 even, 21 to 24, and a couple problems not in the book I want you to simplify. Sine of 40 divided by cosine 50, and tangent 35 minus cotangent 55. Okay, so we'll take a look at that tomorrow. We'll finish up 6-5 tomorrow. And then we'll start our last section of the week on Wednesday.